In 1977, the greatest adventure in space exploration commenced.
Exploration commenced.
We have ignition and we have liftoff.
Our eyes, our minds, our souls are moving out through the universe.
40 years ago, the greatest adventure in space exploration began with the launch of the Voyagers. And we're here today to remember, to celebrate, and to find out what these magnificent machines are still doing.
46 years later, Voyager 1 and its twin Voyager 2 are still alive out there, barreling into the cosmos more than 15 billion miles away. And now, in the blackness of the vast space, the first intrepid spacecraft ever to travel beyond the solar system and reach interstellar space continue their relentless journey, exploring uncharted territories and making groundbreaking discoveries. In a world-shattering revelation, the twins just made an impossible discovery, unveiling interstellar space even weirder than expected. Join us as we dig deep into Voyager's incredible discovery after 46 years in space. In some ways, NASA's twin Voyager probes have become time capsules of their era. Each about the size and weight of a subcompact automobile, the Voyagers epitomize 1970s high-tech. Their computers are weaker than those in today's digital watches, their analog TV cameras more primitive than the ones that shot Laverne and Shirley. But they made history at every planet they reconnoitered, confirming, as Voyager chief scientist Ed Stone put it, that nature is much more inventive than our imaginations. Jupiter, which looks serene through a telescope, was shown by Voyager to have hundreds of raging hurricanes, a glowing aurora at the North Pole, and 3 thin rings. Saturn's rings, previously countable on the fingers of one hand, turned out to include thousands of ringlets and seemingly braided components that theorists had assumed were impossible. Active volcanoes, formerly found only on Earth, turned up in abundance on Jupiter's satellite Io and, astoundingly, on Neptune's Triton, where nitrogen geysers were observed erupting at 40 degrees above absolute zero on the Kelvin scale. 2 of the solar system's most promising environments for finding alien life, Jupiter's icy moon Europa and Saturn's Enceladus, were unveiled by the Voyager mission. Their cores palpitated and heated by tidal interactions. Europa and Enceladus appear to sustain vast, briny oceans beneath the ice, where living organisms might thrive. Perhaps the most poignant gesture of the Voyager mission was its final parting salute to its place of birth. The portrait of the Sun's family of planets, taken in early 1990, included an image of Earth. Carl Sagan, a member of the Voyager imaging team and the captain of the small team that had produced the Golden Record, had proposed this image to the Voyager project in 1981. He eventually called it, appropriately, the pale blue dot. His motivation is expressed in his book of the same name, in which he describes wishing to continue in the tradition begun by the famous Earthrise images of the Apollo program, referring specifically to the one taken from the surface of the Moon by Apollo 17. Then, he continues, "It seemed to me that another picture of the Earth, this one taken from 100,000 times farther away, might help in the continuing process of revealing to ourselves our true circumstance and condition." It had been well understood by the scientists and philosophers of classical antiquity that the Earth was a mere point in a vast encompassing cosmos, but no one had ever seen it as such. Here was our first chance. On August 25, 2012, NASA's Voyager 1 spacecraft was 11 billion miles or 18 billion kilometers from the Sun, and scientists determined that the venerable spacecraft had crossed the boundary between the Sun's influence and the interstellar medium. Now, still going and still sending back data, Voyager 1 and its twin Voyager 2, which joined it in interstellar space in 2018, continue to conduct groundbreaking science. Both Voyagers are now so far from Earth that a one-way radio signal traveling at the speed of light takes almost 23 hours to reach Voyager 1 and near 19 hours to catch up with Voyager 2. Every day, they move away by another 3 to 4 light seconds. Their only link to Earth is NASA's Deep Space Network, a trio of tracking complexes spaced around the globe that enables uninterrupted communication with spacecraft as Earth rotates. As the Voyagers recede from us in space and time, their signals are becoming ever fainter. Earth is a noisy place. Radios, televisions, cell phones, everything makes noise. And so, it gets harder and harder to hear these tiny whispers from the spacecraft. Faint as they are, those whispers still meet astronomers' expectations of what the Voyagers would find as they entered the interstellar phase of the mission. A big science endeavor that consumed some 10,000 work years, the mission has been described as one of the greatest voyages of exploration ever conducted by our species. However, it almost didn't happen. The Voyager mission arose from a happy accident of celestial mechanics. First, Michael Minovich showed that a spacecraft could steal velocity from a planet and use it to accelerate away from the sun. Then, Gary Flandreau applied that logic and showed that probes launched in the late 1970s and 80s could benefit from a rare geometric lineup of the outer planets, skipping world to world on gravitational arcs. Neptune, at the solar system's ragged edge, was suddenly reachable in a dozen years rather than 30. But if the chance was missed, another wouldn't arise until the 22nd century. NASA seized on the opportunity, but shrinking budgets made a grand tour of the outer solar system too expensive. So, the mission was downsized to a $250 million visit to Jupiter and Saturn. But researchers held out hope for a Uranus and Neptune detour. Theoretically, if Voyager 1 worked at Jupiter and Saturn, Voyager 2's trajectory could still be tweaked to visit them. With all options open, Voyager 2 launched on August 20th, 1977, on a long, slow trek into the unknown. Voyager 1 followed on September 5th on a shorter, quicker route. Both spacecraft bristled with scientific gear: cameras, infrared and ultraviolet spectrometers, sensors to map charged particles, cosmic rays and plasmas, a photopolarimeter, and a magnetometer. Nuclear-powered, the Voyager crafts were expected to survive for 5 years. But with some luck and power budget managing, they've exceeded that goal tenfold. Now, renowned as a daring, endless trek to the outer planets and beyond, the Voyager mission became iconic over the years in its scope and meaning. More rite of passage than expedition, more mythic than scientific. The extraordinary images of alien worlds never before seen, and the precognitive sense of being there that they evoked, connected laypeople the world over to Voyager's historic pilgrimage into the unknown, with eternity the final port of call. It was not folly to feel that the mission would gift us all a measure of immortality. The fabled golden record of Voyager heightened the fascination. The two Voyagers each carried a phonograph record of images, music, and sounds representative of our planet, including spoken greetings in 55 languages to any intelligent life form that might find them. This was a message from planet Earth vectored into the Milky Way, a hopeful call across space and time to our fellow galactic citizens. It thrilled to think that news of us and our home planet might be retrieved by some extraterrestrial civilization, somewhere and sometime, in the long future of our galaxy. Because of its never-ending journey, its dazzling scientific discoveries in the solar system, and its human-forward countenance, to participants and onlookers alike, Voyager became symbolic of our acute longing to understand our cosmic place and the significance of our own existence. Up to now, thanks to the twins, humankind has spent more than a decade exploring interstellar space. But as giving humans new insight into some of the big mysteries of our solar system, NASA probes stunned the whole world by revealing that interstellar space even weirder than expected. To make sense of shocking findings, it helps to know that the sun isn't a quietly burning ball of light. Our star is a raging nuclear furnace hurtling through the galaxy at about 450,000 miles an hour as it orbits the galactic center. The sun is also rent through with twisted, braided magnetic fields, and, as a result, its surface constantly throws off a breeze of electrically charged particles called the solar wind. This gust rushes out in all directions, carrying the sun's magnetic field with it. Eventually, the solar wind smashes into the interstellar medium, the debris from ancient stellar explosions that lurks in the spaces between stars. Like oil and water, the solar wind and the interstellar medium don't perfectly mix, so the solar wind forms a bubble within the interstellar medium called the heliosphere. Based on Voyager data, this bubble extends about 11 billion miles from the sun at its leading edge, surrounding the sun, all 8 planets, and much of the outer objects orbiting our star. Good thing too, the protective heliosphere shields everything inside it, including our fragile DNA, from most of the galaxy's highest energy radiation. The heliosphere's outermost edge, called the heliopause, marks the start of interstellar space. Understanding this threshold has implications for our picture of the sun's journey through the galaxy, which in turn can tell us more about the situations of other stars scattered across the cosmos. As Voyager project scientist Ed Stone said, we are trying to understand the nature of that boundary, where these two winds collide and mix. How do they mix, and how much spillage is there from inside to outside the bubble, and from outside the bubble to inside? Scientists got their first good look at the heliopause on August 25, 2012, when Voyager 1 first entered interstellar space. What they began to see left them scratching their heads. For instance, researchers now know that the interstellar magnetic field is about 2 to 3 times stronger than expected, which means, in turn, that interstellar particles exert up to 10 times as much pressure on our heliosphere than previously thought. According to heliophysicist Patrick Cohen, a program scientist at NASA headquarters, it is our first platform to actually experience the interstellar medium, so it is quite literally a pathfinder for us. But for all that Voyager 1 upended expectations, its revelations were incomplete. Back in 1980, its instrument that measured the temperature of plasmas stopped working. Voyager 2's plasma instrument is still working just fine, though. So when it crossed the heliopause on November 5, 2018, scientists could get a much better look at this border. For the first time, researchers could see that as an object gets within 140 million miles of the heliopause, the plasma surrounding it slows, heats up, and gets denser. And on the other side of the boundary, the interstellar medium is at least 54,000 degrees Fahrenheit, which is hotter than expected. However, this plasma is so thin and diffuse, the average temperature around the Voyager probes remains extremely cold. In addition, Voyager 2 confirmed that the heliopause is one leaky border, and the leaks go both ways. Before Voyager 1 passed through the heliopause, it zoomed through tendrils of interstellar particles that had punched into the heliopause like tree roots through rock. However, Voyager 2 saw a trickle of low-energy particles that extended more than 100 million miles beyond the heliopause. Another mystery appeared as Voyager 1 came within 800 million miles of the heliopause, where it entered a limbo-like area in which the outbound solar wind slowed to a crawl. Before it crossed the heliopause, Voyager 2 saw the solar wind form an altogether different kind of layer that, oddly, was nearly the same width as the stagnant one seen by Voyager 1. According to Cohen, that is very, very weird. It really shows us that we need more data. Solving these puzzles will require a better view of the heliosphere as a whole. That's also why NASA has managed to keep these distant sentinels alive. But we know that their unexpectedly lengthy journeys have not been without challenges. Their long years in the harsh environment of space have done a number on the probe, which was designed to last just 4 years. In particular, degraded performance and low power supplies have forced NASA to turn off 6 of its 10 instruments on Voyager 1, and its communication has gotten even spottier than can be explained by the fact that cosmic mechanics mean a signal takes nearly 1 Earth day to travel between humans and the probe. When the latest communications glitch occurred last fall, scientists could still send signals to the distant probe, and they could tell that the spacecraft was operating. But all they got from Voyager 1 was gibberish, what NASA described in December 2023 as a repeating pattern of ones and zeros, like it was trapped in a loop. While the spacecraft can still receive and carry out commands transmitted from the mission team, a problem with that telecommunications unit means no science or engineering data from Voyager 1 is being returned to Earth. After months of study, the Voyager team was able to trace the issue back to a part of the spacecraft's computer system called the Flight Data Subsystem, or FDS, and identified that a particular chip within that system had failed. Mission personnel couldn't repair the chip, but they were able to break the code held on the failed chip into pieces they could tuck into spare corners of the FDS's memory. Scientists then worked to fix errors on the probes by sending software updates across vast distances of space to ensure their continued operation. But updating Voyager's software is a daunting task, akin to performing brain surgery on a patient located 15 billion miles away. The process involves sending new code to the spacecraft's computers, which are designed to operate on machine language, the most basic form of programming. This means that the code must be written in a language that can be directly understood by the hardware, without the aid of an operating system or any fancy programming tools. To overcome these challenges, NASA engineers rely on a combination of ingenuity and resourcefulness. They use assembly language, a low-level programming language that closely resembles machine code, to write the update instructions. This allows them to control the hardware directly and ensure that the code is as efficient as possible. Additionally, they employ pseudocode, a simplified set of commands, to automate repetitive tasks without wasting precious memory. The software updates sent to Voyager are not just patches to fix bugs. They are lifelines that keep these spacecraft alive. Over the years, these updates have addressed various issues, from restarting malfunctioning components to correcting faulty bits of memory. In one instance, a software update saved Voyager 1 from a potential disaster when a piece of hardware failed. The update triggered a fail-safe mechanism, allowing the spacecraft to continue its mission. The ability to update Voyager's software remotely is a testament to NASA's engineering expertise and the resilience of these spacecraft. It demonstrates that even with outdated technology, innovation and resourcefulness can overcome seemingly insurmountable obstacles. In future, Voyager 1 and Voyager 2 venture deeper into interstellar space. The challenges of keeping them operational will only grow. However, NASA remains committed to these missions, determined to extend the lives of these valuable probes for as long as possible. Software updates will continue to play a crucial role in this endeavor, ensuring that these pioneers of space exploration continue their remarkable journey. The story of Voyager's software updates is a reminder of the power of human ingenuity and the enduring legacy of space exploration. It is a testament to our ability to overcome seemingly insurmountable obstacles and push the boundaries of what is possible. While the Voyagers outlive their purpose, they will eventually die. Power levels are so low that only half of their instruments kept on. That's why, over the years, scientists have been convening to discuss how best to keep the spacecraft running for as long as possible, shutting down systems as needed. As of now, Voyager 2 now has 5 remaining functioning instruments, and Voyager 1 has 4. All are powered by a device that converts heat from the radioactive decay of plutonium into electricity. But with the power output decreasing by about 4 watts a year, NASA has been forced into triage mode. 2 years ago, the mission's engineers turned off the heater for the cosmic ray detector, which had been crucial in determining the heliopause transit. Everyone expected the instrument to die. The last 2 Voyager instruments to turn off will probably be a magnetometer and the plasma science instrument. They are contained in the body of the spacecraft, where they are warmed by heat emitted from computers. The other instruments are suspended on a 43-foot-long fiberglass boom. As Suzanne Dodd, who, after a 20-year hiatus from the Voyager team, returned in 2010 as the project manager said, "And so, when you turn the heaters off, those instruments get very, very cold." So, how much longer might the Voyagers last? If everything goes really well, maybe we can get the missions extended into the 2030s. It just depends on the power. That's the limiting point. However, even after the Voyagers are completely muted, their journeys will continue. In another 16 through 700 years, Voyager 1 will pass our nearest neighboring star, Proxima Centauri, followed 3,600 years later by Voyager 2. Then, they will continue to circle the galaxy for millions of years. They will still be out there, more or less intact, eons after our sun has collapsed, and the heliosphere is no more, not to mention one pale blue dot. At some point in their travels, they may manage to convey a final message. It won't be transmitted by radio, and if it's received, the recipients won't be human. The message is carried on another kind of vintage technology. 2 records. Not your standard plastic version, though. These are made of copper coated with gold and sealed in an aluminum cover. Encoded in the grooves of the golden records, as they are called, are images and sounds meant to give some sense of the world the Voyagers came from. A committee led by visionary astronomer Carl Sagan worked for over a year to assemble materials to represent planet Earth. The music garners the most attention as the mixtape for the universe, but it's not the only highlight. One of the sounds of Earth is the manufacture of stone tools, or knapping. This is the most durable technology humans and their ancestors have devised, in use from around 3 million years ago to the present day. For most of human existence, the sound of stone striking stone to detach a sharp-edged cutting flake was heard daily in every community. In one of the 116 images, a black scientist in a lab coat bends over a microscope, tiered earrings falling gracefully from her ears. The earrings were the subject of some debate. Would a future alien viewer recognize the concept of jewelry? It was hoped this image, together with the photomicrograph of cells dividing in image 17, would help viewers figure out that the science of microscopy was known on our planet. People recorded messages in 55 languages. Some are ancient languages, such as Akkadian and Hittite, not heard on Earth for thousands of years. The most common words used are greetings, peace, and friend. The Portuguese greeting spoken by Janet Sternberg says simply, peace and happiness to all. While the golden records are endlessly fascinating, the true cultural significance of the Voyagers lies in their location. The spacecraft are boundary markers showing the physical extent of human engagement with the universe. When the Voyagers cease transmission, it will be like losing a sense. Telescopes can only show us so much. There is no substitute for being there. Who will follow in their path? In fact, there is promising new work underway to pursue a deep space robotic interstellar mission. Called Interstellar Probe, this venture could capture a unified view of our heliosphere out into nearby interstellar space. All of that sounds exceedingly lofty, ambitious, and tough to do. But there's no need to wait for new technology, say advocates. It's here, and one booster of choice for the mission could be NASA's SLS. The new project could launch sometime in the 2030s. It's meant to travel faster and farther than any man-made object has and probably ever will in the foreseeable future. While still in the solar system, the plan is for the spacecraft to visit one or more of the 130 known dwarf planets in the outer reaches of the solar system. There are some clues that some of these icy worlds may have formed as ocean worlds. According to Elena Provornikova, the Interstellar Probe heliophysics lead at APL, the interstellar probe will go to the unknown local interstellar space, where humanity has never reached before. For the first time, we will take a picture of our vast heliosphere from the outside to see what our solar system home looks like. According to early design projections, The interstellar probe should travel at a speed at least twice as fast as Voyager 1, which should help it travel about 375 astronomical units, or 34 billion miles, in its first 50 years. If it manages to travel another 50 years, the spacecraft could end up covering more than 800 astronomical units, which amount to a staggering 74 billion miles. Though impressive, that distance isn't actually a lot by astronomical standards. Bear in mind that Proxima Centauri, the closest star to our solar system, is about 25 trillion miles away. It would probably take more than 30,000 years to reach Proxima Centauri with our current tech. That's how far behind we are from the feats casually imagined in science fiction and popular media. You gotta start somewhere, though, which is why NASA wants a continued presence in interstellar space. Interstellar missions are a different beast from anything NASA or any other space agency, for that matter, has attempted before. It's not that they're necessarily more technically challenging than landing an astronaut on the moon or operating a rover on Mars. It's just that their timescale is so large, they will outlive the original members of the mission. This brings with it a novel suite of challenges that come with passing the baton to a new generation of scientists. The mission will also have to somehow safely store hardware spare parts, as well as the software they code now, so that engineers have the debugging tools required to solve a possible malfunction even 100 years from now. You gotta think ahead, and that may involve imagining the unthinkable. After all, with Interstellar Probe, scientists believed that we will be learning a great deal more than the Voyagers could tell us every year that this mission flies. Not only about the interstellar medium, but also about long-life electronics, deep space communications, and the nature of our sun's travel through the galaxy with its protective heliosphere. We'll also have plentiful targets for study as Interstellar Probe moves through the outer solar system and its abundant Kuiper Belt objects. Although the proposed mission is still in its planning phase, with an estimated cost of around $1.5 billion, scientists hope to attach some new Easter eggs like Voyager's golden record. Either way, for most of humanity's history, we didn't believe ourselves to be alone. We filled the heavens with gods, monsters, and mythic creatures. It is only in the modern age that our species has started to worry about its place in the universe. But what could happen if a spacecraft might find when looking at a far-off planet for signs of intelligent life? Well, there was plenty to see. Our technology creates an intriguing mess. Lights blaze and heat islands glow in paved-over urban areas. Atmospheric gases ebb and flow, evident today not only in rising concentrations of carbon dioxide and methane, but also in clouds of floating industrial byproducts. Sometimes there are radiation leaks. And all the while, billions of gadgets and antennas cast off a buzzing planetary swarm of electromagnetic transmissions. Would other planets' civilizations be like ours? Would they create the same telltale chemical and electromagnetic signs, what scientists have recently begun calling techno-signatures, that Galileo detected? The search for intelligence beyond Earth has long been defined by an assumption that extraterrestrials would have developed radio technologies akin to what humans have created. In some early academic papers on the topic, dating to the late 1950s, scientists even posited that these extraterrestrials might be interested in chatting with us. But over time, the search for signals from deep space has become more agnostic. Rather than looking for direct calls to Earth, telescopes now sweep the sky, searching billions of frequencies simultaneously for electronic signals whose origins can't be explained by celestial phenomena. At the same time, the search for intelligent life has turned in a novel direction. Scientists' work now is not about communicating with aliens, nor is it meant to contribute to research on extraterrestrial radio transmissions. They are instead thinking mainly about the atmospheres of distant worlds and what those might tell us. This line of inquiry might not have been productive just a few years ago, but several advances have made the search for techno-signatures feasible. The first, thanks to new telescopes and astronomical techniques, is the identification of planets orbiting distant stars. As of now, NASA's confirmed tally of such exoplanets was more than 5,600, and the number tends to grow by several hundred a year. Because there are probably at least 100 billion stars in the Milky Way galaxy, and an estimated 100 billion galaxies in the universe, the potential candidates for life, as well as for civilizations that possess technology, may involve numbers almost too large to imagine. Perhaps more important, our tools keep getting better. Several other powerful ground and space-based instruments are being developed that will allow us to view exceedingly distant objects for the first time or view previously identified objects in novel ways. For instance, with things like the James Webb Space Telescope and some of the other telescopes, we're beginning to be able to probe atmospheres looking for much smaller signals. And this is something we just couldn't have done before. What's interesting, when it comes to searching for life on exoplanets, Webb is a testing ground for a successor telescope that will be bigger and better. In January 2023, Dr. Mark Clampin, the director of NASA's Astrophysics Division, told a meeting of the American Astronomical Society that the successor to Webb would be called the Habitable Worlds Observatory, or HWO for short. No one knows what HWO will look like, as the telescope is still in its early design stages. But some basic requirements are already in place, thanks to the 2020 Astrophysics Decadal Survey, a community-authored report that sets priorities for NASA's next 10 years. HWO would have a mirror about the size of James Webb's and be positioned at the same location, the second Lagrange point, a gravitationally stable spot located 1 million miles from Earth. Like Hubble, HWO would be serviceable, meaning future astronauts could journey to the telescope for repairs and upgrades. Also like Hubble, HWO would gather light in shorter, visible, and ultraviolet wavelengths, where certain biosignatures are more pronounced. Shorter wavelengths also work best with a key piece of technology needed to directly observe exoplanets, a coronagraph. Coronagraphs are used to block the light of stars, revealing fainter nearby objects. Imaging an exoplanet is like searching for a firefly next to a spotlight. Seeing smaller Earth-sized planets will require the most advanced coronagraph ever built. A technology demonstration coronagraph for HWO will fly on the upcoming Roman Space Telescope. Rather than blocking a star's light with a disk, Roman's coronagraph uses a series of mirrors and masks to separate light from an exoplanet from that of its host star. The mirrors are so precise that they can make adjustments smaller than the width of a strand of DNA. As extraordinary as that sounds, the requirements for the optics within HWO's coronagraph may be even stricter, requiring corrections on the order of tens of picometers, smaller than the width of an atom. Building such a next-generation observatory to hunt for life and advance our understanding of the cosmos will be a challenging and costly project. The telescope would not launch until at least the early 2040s, but it will be worth the wait. Anyway, one day in the not-so-distant future, the observatory could train its eyes on a star system not unlike our own, and pick out the first signs of life on another world. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Way out in interstellar space, humanity's most distant messenger wanders through the universe.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Launched way back in 1977, NASA's Voyager 1 is remembered as one of the greatest achievements in exploration. The mission not only transformed our knowledge of Jupiter, Saturn, and their dozens of moons, it also gave us our first close-up look at the strange and wondrous planets Uranus and Neptune. Even when you're watching this video, the two Voyager probes are still operating and traveling into interstellar space where no spacecraft or anything else touched by human hands has ever gone before. However, on track to conquer the new territory, there's something terrifying is happening on board one of the most iconic NASA spacecraft of the 20th century. It catches spooky signals from interstellar space. Does Voyager just encounter an unknown force? If so, are those signals messages aliens sent to us? But could it be a friendly greeting or a threat? Join us as we dig deep into the Voyager's unimaginable trip and the puzzling signal that has overwhelmed scientists. In the decades since the two craft were launched into space, Voyager 1 has traveled more than 15 billion miles, while Voyager 2 has hit the 12 billion miles mark. It's worth pausing to reflect on the vision that inspired Voyager, its greatest achievements, and its enduring legacy. How the two probes and their findings inspired those that followed, and how they continue to influence NASA missions today. In some quieter moments, we think about a time, billions of years from now, when our sun has become a red giant. By then, Earth will no longer be habitable and, in order to survive, humans will have left the nest for another home, following a path forged by the Voyager missions. It's humbling and inspiring to think that, even then, the Voyagers will still be Earth's ambassadors. Each one a time capsule from an era when audacious explorers on our pale blue dot reached out to the stars beyond our solar system. Not only has the science produced by the Voyager mission been captivating, the probes themselves captured the world's imagination by each carrying a greeting for extraterrestrial civilizations in the form of the Golden Records. While Pioneers 10 and 11 each carried small metal plaques detailing their origin and date of launch, the Voyager's Golden Records were considerably more ambitious. The twin phonograph records brim with images and sounds that provide a snapshot of the diversity of life and culture on Earth to anyone that might discover them. As Carl Sagan noted, the launching of this bottle in the cosmic ocean says something very hopeful about life on this planet. But the Voyager mission was as ambitious as it gets. Collectively, the Voyagers visited more planets, discovered more moons, and imaged more places than any other spacecraft in NASA history. One of the questions many often asked is, why were there two Voyagers? In fact, Voyager was an early NASA mission, at a time when flight systems were known to suffer many anomalies that would put them in safe mode, a condition that typically shuts down all science instruments and looks for commands from Earth. Since the Voyager missions were flybys, anomalies that would require a lot of time to diagnose and correct could result in us missing an encounter and all the science that might derive from it. By having two spacecraft, we could increase the odds of the mission's success. The same strategy was employed with the Mars exploration rovers, Spirit and Opportunity. Having two rovers not only provides a redundancy, but also gives us a bigger margin for error. It quickly became clear that this 1-2 punch strategy was the best one to adopt. Voyager 1's scan platform, the swivel that moves its cameras and instruments from side to side, became stuck for several weeks in 1978. The same platform became stuck on Voyager 2's as the spacecraft was pulling away from its closest approach with Saturn. Fortunately, Voyager 2 produced fantastic results at Saturn despite the technical problems, but the anomalies reinforced the value of redundancy and having a second craft as a backup. Over their grand tours of the solar system, the Voyagers took tens of thousands of images and measurements that significantly changed our understanding of the outer planets. At Jupiter, they gave us our first detailed ideas of how the planet's atmosphere moves and evolves. showing that the Great Red Spot was a counterclockwise rotating storm that interacted with other, smaller storms. They were also the first missions to spot a faint, dusty ring around Jupiter. Finally, they observed some of Jupiter's moons, discovering Io's volcanism, finding the linear features on Europa that were among the first hints that it might have an ocean beneath its surface, and granting Ganymede the title of largest moon in the solar system, a superlative that was previously thought to belong to Saturn's moon Titan. Next, each spacecraft flew past Saturn, where they measured the composition and structure of Saturn's atmosphere, and Voyager 1 also peered into Titan's thick haze. Its observations led to the idea that Titan might have liquid hydrocarbons on its surface, a hypothesis that has since been verified by other missions. When the two missions observed Saturn's rings, they found the gaps and waves that are well known today. Voyager 1 also spotted 3 previously unknown moons orbiting Saturn: Atlas, Prometheus, and Pandora. After this, Voyager 1 headed out of the solar system, while Voyager 2 headed toward Uranus. There, it found 11 previously unknown moons and 2 previously unknown rings. Many of the phenomena it observed on Uranus remained unexplained, such as its unusual magnetic field and an unexpected lack of major temperature changes at different latitudes. Voyager 2's final stop, 12 years after it left Earth, was Neptune. When it arrived, it continued its streak of finding new moons with another haul of 6 small satellites, as well as finding rings around Neptune. As it did at Uranus, it observed the planet's composition and magnetic field. It also found volcanic vents on Neptune's huge moon Triton before it joined Voyager 1 on the way to interstellar space. For those who don't know, interstellar space begins at the heliopause, where the solar wind, a flow of charged particles released by the sun, is too weak to continue pushing against the interstellar medium, and the pressure from the two balances out. Voyager 1 left the heliosphere in August 2012, popping free into interstellar space. The discovery was made public in a study published in the journal Science the following year. The results came to light after a powerful solar eruption was recorded by Voyager 1's plasma wave instrument between April 9 and May 22, 2013. The eruption caused electrons near Voyager 1 to vibrate. From the oscillations, researchers discovered that Voyager 1's surroundings had a higher density than what is found just inside the heliosphere. It seems contradictory that electron density is higher in interstellar space than it is in the Sun's neighborhood. But researchers explained that, at the edge of the heliosphere, the electron density is dramatically low compared with locations near Earth. Researchers then backtracked through Voyager 1's data and nailed down the official departure date to August 25, 2012. The date was fixed not only by the electron oscillations, but also by the spacecraft's measurements of charged solar particles. On that fateful day, which was the same day that Apollo 11 astronaut Neil Armstrong died, the probe saw a 1,000-fold drop in these particles and a 9% increase in galactic cosmic rays that come from outside the solar system. At that point, Voyager 1 was 11.25 billion miles from the Sun, or about 121 astronomical units. 1 astronomical unit is the average Earth-Sun distance, about 93 million miles. But interstellar space, the space between the stars, isn't just empty space. There's a lot of stuff out there. Roughly 70% of the interstellar space is hydrogen. Helium makes up about 28%, formed in the Big Bang that set our universe into motion. The other 2% of stuff in interstellar space is heavier gases and dust, consisting of the other elements made inside stars and spewed into space by supernovae. The material in interstellar space is very spread out. It's denser in some places than in others, but a typical density is about 1 atom per cubic centimeter. Still, even the most dense regions of interstellar space count as vacuum compared with our earthly air. Our sun controls the conditions around our solar system, but outside of that is interstellar space and all that it contains. Astronomers call this space between the stars the interstellar medium. The interstellar medium is where stars are made. Without it, we wouldn't exist. If there weren't thick and thin spots that condensed into thicker patches that eventually became stars, the whole universe would just be a cloud of boring, cold, lifeless gas. The thick parts of the interstellar medium are called molecular clouds, often referred to as stellar nurseries, the places where stars are born. The first stars didn't have planets because there weren't any materials in interstellar space beyond hydrogen and helium. But over the billions of years of our universe's history, that has changed. It changed because stars themselves make increasingly more complex elements in their interiors. When the most massive stars grow old and die, they explode as supernovae, releasing their elements into interstellar space. Thus, it has become possible for stars to form with planets, and for at least one planet we know of, Earth, to harbor living things. Given the contents of interstellar space and process by which stars and planets are born, it seems highly likely that other planets have living things too. This is also why scientists were extremely excited when Voyager flew beyond the heliopause and became the first human-made object to explore this new territory, where no spacecraft, or anything else touched by human hands, has ever gone before. In there, scientists expect the greatest space explorer could answer the long-standing question that has captivated human imagination for centuries. Are we alone in the universe? In the thousands of years humanity has been contemplating the cosmos, we are the first people to know one thing for sure. The stars beyond our sun are teeming with planets. They come in many varieties, and a good chunk of them are around the size of Earth. However, like most scientific questions, getting an answer to this one just breeds more questions. Which, if any, of these exoplanets harbors some form of life? How quickly does life get its start, and how long does it last? The universe's eerie silence has its own name, the Fermi paradox. Physicist Enrico Fermi famously posed the question, where is everybody? Even at slow travel speeds, the universe's billions of years of existence allow plenty of time for intelligent, technological life forms to traverse the galaxy. Why, then, is the cosmos so quiet? Meanwhile, exoplanet discoveries over the past 2 decades have filled in a few of the terms in the much-debated Drake equation, a chain of numbers that might one day tell us how many intelligent civilizations we can expect to find. Most of its terms remain blank: the fraction of planets with life, with intelligent life, with detectable technology, but the equation itself suggests we might one day arrive at an answer. It feels at least a little more hopeful than Fermi's silence. We stand at a crossroads in the search for life. We've found thousands of planets in our Milky Way galaxy, a large fraction of them in Earth's size range and orbiting in their star's habitable zones, the distance from the star at which liquid water could exist on the surface. We know the galaxy likely holds trillions of planets. Our telescopes in space and on the ground and our remote sensing technology grow ever more powerful. Yet so far, the only life we know of is right here at home. For the moment, we're staring into the void, hoping someone is staring back. Since flying into interstellar space, Voyager 1 has sent back a variety of valuable information about conditions in this zone of the universe. Its discoveries include showing that cosmic radiation out there is very intense, and demonstrating how charged particles from the sun interact with those emitted by other stars. The spacecraft's capabilities continue to astound engineers. In December 2017, for example, NASA announced that Voyager 1 successfully used its backup thrusters to orient itself to talk with Earth. The trajectory correction maneuver thrusters hadn't been used since November 1980 during Voyager 1's flyby of Saturn. Since then, the spacecraft had primarily used its standard attitude control thrusters to swing the spacecraft in the right orientation to communicate with Earth. As the performance of the attitude control thrusters began to deteriorate, NASA decided to test the trajectory correction maneuver thrusters, an idea that could extend Voyager 1's operational life. That test ultimately succeeded, and in an unimaginable finding, the Allen Telescope Array in California detected signal from the Voyager 1 probe, the NASA satellite launched 46 years ago that is currently speeding toward the outer edges of the solar system, way beyond the orbit of Pluto. Allen Telescope Array, a recently refurbished radio observatory near San Francisco in California dedicated to the search for extraterrestrial life, made contact with the Voyager 1 probe using 20 of its 42 dish antennas, which are each over 6.1 meters wide. The telescope recorded 15 minutes of data, according to a statement, which were stored on a disk. The statement didn't provide any additional information about the signal it caught, but many strongly believed that there has been an encounter between the spacecraft and some mysterious force in space. One of the horrifying scenarios outlined also said that aliens had hijacked Voyager 1, and the signals it sent back to Earth were messages that higher civilizations wanted to send to humans. But will it be a friendly greeting or a threat? We just don't know. So, let's be cautious. Anyway, space is full of mysteries and surprises, so be prepared for the worst situations. Back to Voyager 1, currently located about 15.1 billion kilometers away from Earth, 162 times the Sun-Earth distance, the probe is still being tracked by NASA's Deep Space Network, sending a meager 160 bits per second of data back home. For comparison, a regular home broadband connection is measured in megabits per second, that is millions of bits per second. However, all Voyager's instruments are powered by a device that converts heat from the radioactive decay of plutonium into electricity. But with the power output decreasing by about 4 watts a year, NASA has been forced into triage mode. A few years ago, the mission's engineers turned off the heater for the cosmic ray detector, which had been crucial in determining the heliopause transit. Everyone expected the instrument to die. The last 2 Voyager instruments to turn off will probably be a magnetometer and the plasma science instrument. They are contained in the body of the spacecraft, where they are warmed by heat emitted from computers. The other instruments are suspended on a 43-foot-long fiberglass boom, and so when you turn the heaters off, those instruments get very, very cold. So how much longer might the Voyagers last? Just a couple of few years. If everything goes really well, maybe we can get the missions extended into the 2030s. It just depends on the power. That's the limiting point. The only piece of good news is even after the Voyagers are completely muted, their journeys will continue. In another 16,700 years, Voyager 1 will pass our nearest neighboring star, Proxima Centauri, followed 3,600 years later by Voyager 2. Then they will continue to circle the galaxy for millions of years. They will still be out there, more or less intact, eons after our sun has collapsed and the heliosphere is no more, not to mention one pale blue dot. At some point in their travels, they may manage to convey a final message. It won't be transmitted by radio, and if it's received, the recipients won't be human. The message is carried on another kind of vintage technology, 2 records. Not your standard plastic version, though. These are made of copper, coated with gold, and sealed in an aluminum cover. Encoded in the grooves of the golden records, as they are called, are images and sounds meant to give some sense of the world the Voyagers came from. There are pictures of children, dolphins, dancers, and sunsets. The sounds of crickets, falling rain, and a mother kissing her child, and 90 minutes of music including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good. And there is a message from Jimmy Carter, who was the U.S. president when the Voyagers were launched. We cast this message into the cosmos. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination, and our goodwill in a vast and awesome universe. The records were designed to last, meant to survive perhaps 1 billion years in space. Beneath the golden sheen is a protective aluminum casing, and, below that, the engraved copper discs themselves. But to truly understand how long these objects may survive, you have to know what conditions they'll experience, and that means knowing where they will be, because there are few phenomena that could actually act to damage the spacecraft. It's a grim scenario, dust pounding into the Voyagers at a speed of a few miles or kilometers per second. As Nick Oberg, a doctoral candidate at the Kaptein Astronomical Institute in the Netherlands, said, "The grains will act as a steady rain that slowly chips away at the skin of the spacecraft. A dust grain, only 1,000th of a millimeter across, will still leave a small vaporized crater when it impacts." Voyager 1's vertical oscillations mean that spacecraft will spend more time above and below the plane of the galaxy, where the clouds are thickest. Oberg and his colleagues simulated thousands of times over the paths of the two spacecraft and their encounters with the dust clouds, modeling the damage the golden records would incur along the way. That work also requires taking into consideration the possibility that a cloud's gravity might tug at one of the Voyager's trajectories, Oberg said. The clouds have so much mass concentrated in one place that they actually may act to bend the trajectory of the spacecraft and fling them into new orbits, sometimes much farther out, sometimes even deeper toward the galactic core. Both golden records have good odds of remaining legible, since their engraved sides are tucked away against the spacecraft bodies. The outer surface of Voyager 1's record is more likely to erode away, but the information on Voyager 2's record is more likely to become illegible. And according to Oberg, the main reason for this is because the orbit that Voyager 2 is flung into is more chaotic, and it's significantly more difficult to predict with any certainty of exactly what sort of environment it's going to be flying through. But despite the onslaught and potential detours, Oberg concluded that both golden records are highly likely to survive at least partially intact for a span of over 5 billion years. After those 5 billion years, modeling is tricky. That's when the Milky Way is due to collide with its massive neighbor, the Andromeda Galaxy, and things get messy. The orderly spiral shape will be severely warped and possibly destroyed entirely. The Voyagers will be caught up in the merger, with the details difficult to predict so far in advance. Meanwhile, the vicarious sightseeing continues. Oberg and his colleague calculated that in this 5 billion year model-friendly period, each of the Voyagers likely visits a star, besides our Sun, within about 150 times the distance between Earth and the Sun, or 3 times the distance between the Sun and Pluto, at the dwarf planet's most distant point. Precisely which star that might be, however, is tricky. It may not even be a star we know today. As Oberg explained, while neither Voyager is likely to get particularly close to any star before the galaxies collide, the craft are likely to at least pass through the outskirts of some star system. The very strange part is that that actually might be a system that does not yet exist, of a star that has yet to be born. Such are the perils of working on a scale of billions of years. From here, the Voyager's fate depends on the conditions of the galactic merger. The collision itself might kick a spacecraft out of the newly monstrous galaxy, a 1 in 5 chance, he said, although it would remain stuck in the neighborhood. If that occurs, the biggest threat to the golden records would become collisions with high-energy cosmic rays and the odd molecule of hot gas, Oberg said. These impacts would be rarer than the dust that characterized their damage inside the Milky Way. Inside the combined galaxy, the Voyager's fate would depend on how much dust is left behind by the merger. Oberg said that may well be minimal, as star formation and explosion both slow, reducing the amount of dust flung into the galaxy. Depending on their luck with this dust, the Voyagers may be able to ride out trillions of trillions of trillions of years, long enough to cruise through a truly alien cosmos. Such a distant time is far beyond the point where stars have exhausted their fuel and star formation has ceased in its entirety in the universe. The Voyagers will be drifting through what would be, to us, a completely unrecognizable galaxy free of so-called main sequence stars, populated almost exclusively by black holes and stellar remnants, such as white dwarfs and neutron stars. It's a dark future. The only source of significant illumination in this epoch will be supernovas that results from the once-in-a-trillion-year collision between these stellar remnants that still populate the galaxy. Our work, found on these records, thus may bear witness to these isolated flashes in the dark. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Have you ever wondered what lies beyond the planets of our solar system? How far can we explore the vastness of space? What mysteries await us in the interstellar medium? These are some of the questions that motivated the Voyager 1 and 2 missions, two twin spacecraft that were launched in 1977 and are still operating today, more than 46 years later. To date, the twins are the most successful and the longest-running missions in the history of space exploration. They have traveled farther than any other spacecraft, and they have visited more worlds than any other mission. They have made countless discoveries that have changed our view of the solar system and the cosmos, and they have inspired generations of scientists. But their unimaginable journey hasn't stopped yet. Those little mechanical masterminds have been cutting a path through space for nearly half a century, and they're still going strong. They might even get to another star system one day, a few tens of thousands of years from now. Join us as we dig deep into the most amazing scientific discoveries that these spacecraft have made and how they have transformed our understanding of the cosmos. The solar system is a vast expanse of space that consists of the sun, planets, moons, asteroids, comets, and other celestial bodies. It is a collection of objects that revolve around the sun due to its gravitational pull. The sun, being the central and most massive component, provides light, heat, and energy to the entire solar system. The main components of the solar system are the Sun, 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, 5 officially recognized dwarf planets, Pluto, Eris, Haumea, Makemake, and Ceres, numerous moons, thousands of asteroids, countless comets, and various other small bodies. The formation of the solar system began approximately 4.6 billion years ago. It is believed that the solar system evolved from a vast cloud of gas and dust called the solar nebula. As the nebula collapsed under its own gravitational force, it formed a rotating disk that eventually gave birth to the sun and the planets. The process of planetary formation involved the accretion of smaller particles, known as planetesimals, which collided and merged over time, gradually forming larger bodies. Eventually, these bodies became the planets and other celestial objects that make up our solar system today. The solar system is an enormous place, spanning a distance of approximately 5.9 billion miles from the Sun to the outermost regions of the Oort cloud. The Sun, with a diameter of about 864,000 miles, accounts for over 99% of the total mass of the solar system. The planets vary greatly in size, with the largest planet, Jupiter, being more than 11 times the diameter of Earth. To grasp the vast size and scale of the solar system, consider this. If the Sun were the size of a basketball, then the Earth would be the size of a peppercorn located 26 meters away, and Pluto, the farthest recognized object, would be the size of a pinhead located 2 kilometers away. The exploration of the solar system began with early space missions in the mid-20th century. the Soviet Union's Luna program successfully sent robotic missions to the moon, paving the way for future crewed missions. The United States, through its Gemini and Apollo programs, achieved the first human landing on the moon in 1969, a milestone in human space exploration. The space age, which started in 1957 with the launch of the Soviet satellite Sputnik, saw significant advancements in space exploration technology. It allowed for the exploration of planets, moons, asteroids, and comets through both robotic and crewed missions. The study of the solar system expanded rapidly during this era, providing valuable insights into the nature and formation of celestial bodies. But the landmark mission contributed to our understanding and exploration of the solar system is the Voyagers. The Voyager 1 and 2 spacecraft were designed to take advantage of a rare alignment of the 4 giant planets of our solar system: Jupiter, Saturn, Uranus, and Neptune. This alignment occurs only once every 175 years, and it allows a spacecraft to use the gravity of each planet to boost its speed and change its trajectory, enabling it to visit all 4 planets in a single mission. This is known as the Grand Tour, and it was a unique opportunity to explore the outer solar system in detail. The duo were launched in 1977, 2 weeks apart from each other. Voyager 2 was actually launched first, on August 20th, followed by Voyager 1 on September 5th. The reason for this was that Voyager 1 had a faster and shorter trajectory, and it would reach Jupiter and Saturn before Voyager 2. This way, Voyager 1 could test the instruments and the communication system and send back valuable data that could help Voyager 2 adjust its course and optimize its observations. The first destination of the Voyager spacecraft was Jupiter, the largest and most massive planet in our solar system. Voyager 1 arrived at Jupiter in March 1979, followed by Voyager 2 in July. The spacecraft took thousands of images and measurements of the planet and its moons, revealing many surprising features. For example, they discovered that Jupiter has a powerful magnetic field and a complex system of rings, composed of dust and debris from its moons. They also found that Jupiter's atmosphere is turbulent and stormy, with winds reaching up to 600 km/h, and a giant red spot that is actually a persistent hurricane larger than Earth. But perhaps the most astonishing discovery was that one of Jupiter's moons, Io, has active volcanoes that spew sulfur and other materials into space. Io is the most volcanically active body in the solar system, and its eruptions are caused by the intense gravitational pull of Jupiter and its other moons, which deform and heat up Io's interior. The Voyager spacecraft captured stunning images of Io's volcanoes, some of which were erupting at the time of the flyby. The next stop of the Voyager spacecraft was Saturn, the second largest and the most beautiful planet in our solar system. Voyager 1 reached Saturn in November 1980, followed by Voyager 2 in August 1981. The spacecraft took spectacular images and measurements of the planet and its rings, which are composed of billions of ice and rock particles of different sizes and shapes, ranging from dust grains to boulders. The rings are divided into several sections by gaps and resonances with Saturn's moons, and they exhibit complex structures and patterns such as waves, braids, spokes, and arcs. The Voyager spacecraft also discovered several new moons of Saturn, bringing the total number to 22 at the time. One of the most intriguing moons was Titan, the largest and the only one with a thick atmosphere. The atmosphere of Titan is mostly nitrogen, with traces of methane and other organic compounds. The Voyager spacecraft could not see through the dense clouds of Titan, but they detected that the moon has a surface pressure of about 1.5 times that of Earth, and a surface temperature of about 180 degrees. They also found that Titan has a weak magnetic field and a possible subsurface ocean of water and ammonia. The Voyager 1 spacecraft ended its planetary tour at Saturn, as it was diverted to fly close to Titan and obtain more data. This maneuver caused Voyager 1 to leave the plane of the solar system and head towards interstellar space. The Voyager 2 spacecraft, however, continued its journey to the next two planets, Uranus and Neptune. Uranus is the third largest and the most tilted planet in our solar system. Its axis of rotation is almost parallel to the plane of its orbit, which means that it rotates on its side. This causes extreme seasons on Uranus, with each pole facing the sun for 42 years, followed by 42 years of darkness. Voyager 2 arrived at Uranus in January 1986, and it was the first and only spacecraft to visit this planet. The spacecraft took images and measurements of Uranus and its moons, revealing a bland and featureless planet with a faint ring system and a weak magnetic field that is tilted 60 degrees from its axis of rotation. The spacecraft also discovered 10 new moons of Uranus, bringing the total number to 15 at the time. One of the most interesting moons was Miranda, which has a bizarre and varied terrain with ridges, valleys, cliffs, and craters, suggesting a violent and complex geological history. Neptune is the fourth largest and the most distant planet in our solar system. It is a cold and windy world, with the fastest winds in the solar system, reaching up to 2,100 km/h. Voyager 2 reached Neptune in August 1989, and it was also the first and only spacecraft to visit this planet. The spacecraft took images and measurements of Neptune and its moons, revealing a beautiful blue planet with a dynamic atmosphere and a powerful magnetic field that is tilted 47 degrees from its axis of rotation. The spacecraft also discovered 6 new moons of Neptune, bringing the total number to 8 at the time. The most fascinating moon was Triton, which is the largest and the only one that orbits in the opposite direction of Neptune's rotation. Triton has a thin nitrogen atmosphere and a frozen surface covered with ice, snow, and geysers that spout nitrogen gas and dust. The Voyager 2 spacecraft completed its grand tour of the outer planets at Neptune, and it also left the plane of the solar system and headed towards interstellar space. The Voyager 1 and 2 spacecraft have visited more planets than any other mission in history, and they have made countless discoveries that have revolutionized our knowledge of the solar system and its diversity. After their planetary encounters, the Voyager 1 and 2 spacecraft continued their journey to the edge of the solar system and beyond. Their new mission, called the Voyager Interstellar Mission, is to explore the outermost regions of the Sun's influence and to enter the interstellar medium, the space between the stars. The spacecraft are still communicating with Earth and sending back valuable data, despite being more than 20 billion kilometers away from us. The Sun is the source of light and heat for our solar system, but it also produces a stream of charged particles called the solar wind, which flows outward in all directions. The solar wind creates a bubble around the Sun and the planets, called the heliosphere, which protects us from the interstellar radiation and cosmic rays. The heliosphere has several layers and boundaries, which the Voyager spacecraft have been exploring and crossing. The first boundary is the termination shock, where the solar wind slows down abruptly as it encounters the pressure of the interstellar medium. The Voyager 1 spacecraft crossed the termination shock in December 2004, followed by Voyager 2 in August 2007. The second boundary is the heliopause, where the solar wind stops completely and the interstellar medium begins. The Voyager 1 spacecraft crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. The Voyager 2 spacecraft crossed the heliopause in November 2018, joining its twin in the interstellar realm. The third boundary is the bow shock, where the interstellar medium is compressed and heated by the motion of the heliosphere through the galaxy. However, the Voyager spacecraft have not detected this boundary yet, and some scientists think that it may not exist at all, as the heliosphere may be moving too slowly to create a shockwave. The Voyager spacecraft are now exploring the interstellar medium, which is not empty, but filled with gas, dust, magnetic fields, and cosmic rays. The spacecraft are measuring the properties and variations of these components and comparing them with the conditions inside the heliosphere. The spacecraft are also searching for signs of other stars and their heliospheres, which may be nearby or far away. The Voyager spacecraft are expected to keep operating until the mid-2020s, when their power sources will run out and they will go silent. However, they will continue to travel through the interstellar medium, carrying a message for any potential alien civilization that may encounter them. The message is a golden record attached to each spacecraft, which contains sounds and images of Earth and its life forms, as well as greetings in 55 languages and music from different cultures. The golden record is a time capsule and a testament of our existence and our curiosity as we reach out to the unknown. And scientists expect one day Voyager's golden record could answer the question, are we alone in the universe? Are we alone? This question has plagued humankind since time immemorial. And yet, we still don't have a conclusive answer. Despite our incredible technological advancements, we have never received a credible radio signal from, or even the teeniest trace of, extraterrestrial life beyond Earth. The quest to determine if anyone or anything is out there has gained greater scientific footing in the nearly half-century since the article titled "Seeking an End to Cosmic Loneliness," published in the New York Times in 1977. That article described physicists' attempts to pick up radio messages from aliens' publication. The endeavor, known as the Search for Extraterrestrial Intelligence, or SETI, was still in its early stages, and its proponents were struggling to persuade their peers and Congress that the idea was worth funding. Back then, astronomers had yet to spot a single planet outside our solar system. Now we know the galaxy is teeming with a diversity of worlds. Our planet's oceans were once considered exceptional, whereas evidence today suggests that numerous moons in the outer solar system host subsurface waters. Our notion of the range of environments where life could exist has also expanded thanks to the discovery on Earth of extremophile organisms that can thrive in places far hotter, saltier, acidic, and more radioactive than previously thought possible, including creatures living around undersea hydrothermal vents. We're now getting closer than ever before to learning how common living worlds like ours actually are. New tools, including machine learning and artificial intelligence, could help scientists look past their preconceived notions of what constitutes life. Future instruments will sniff the atmospheres of distant planets and scan samples from our local solar system to see if they contain telltale chemicals in the right proportions for organisms to prosper. As Ravi Kopparapu, a planetary scientist at NASA's Goddard Space Flight Center in Maryland, shared, "I think within our lifetime we will be able to do it. We will be able to know if there is life on other planets." Two of the most iconic insights related to the possibility of technological civilizations existing elsewhere in the universe are the Fermi paradox and the Drake equation, which were formulated by Enrico Fermi and Frank Drake, respectively. The Fermi paradox attempts to address the question, where is everybody? By most accounts, Fermi asked this deceptively simple question in 1950 during lunch with colleagues. The simple question has since spurred scientists to better understand the possible reasons that we haven't heard from any technologically advanced alien civilizations. As Harshini Sunil, an astronomy and physics undergraduate student at the University of Colorado Boulder, said, "The Fermi paradox is interesting because it contradicts the possibility of advanced life in our galaxy. If advanced civilizations have existed before us, then they would have had ample time to develop interstellar travel and would have made it to Earth. If we invented interstellar travel, where would we go first? We have the predictions of places for life, but they are still hundreds or more light years away. Even if we could travel at the speed of light, there is no guarantee that we will know exactly where to look. It's like hunting for needles in a haystack." Thus, after all, for Sunil and many researchers, the possibility of finding advanced life is black or white. There is so much we first need to discover and learn before we can start predicting where and if advanced life exists. While the Fermi paradox asks why we haven't heard from anyone, the Drake equation attempts to spin a more optimistic approach to this conundrum. The Drake equation is an attempt to quantify the total number of technological civilizations that might currently exist in the cosmos. To do this, the equation factors in astronomical, biological, psychological, and technological elements. However, because the exact values for each of the equation's variables are largely unknown, the Drake equation tends to estimate the number of potential technological civilizations at anywhere between 1, that's us, and 1,000,000. So, it could be said that the Drake equation serves both as a reality check and a hopeful mantra for those involved in the search for life elsewhere. As Franny Edmondson, an astrobiology senior undergraduate student in the Department of Aerospace Physics and Space Sciences at the Florida Institute of Technology, says, running through its argument gives you a bleak outlook on our galaxy's intelligent population, but the objectiveness of the equation is necessary for research. Not every stray signal we detect will be an ET neighbor shouting between solar systems. Still, I remain hopeful when considering the Drake equation because of our own existence. Even with slim chances, our intelligent civilization exists, so there is the potential for others. But the question remains, are we alone? Well, first and foremost, we all have accepted that while humans have a long history of speculating about distant worlds, for much of that time, actual evidence was in short supply. The first planets around other stars, known as exoplanets, were discovered in the early 1990s, but it took until the launch of NASA's Kepler Space Telescope in 2009 for astronomers to understand how common they were. Kepler carefully monitored hundreds of thousands of stars, looking for tiny dips in their brightness that could indicate planets passing in front of them. The mission helped the number of known exoplanets rise from a mere handful to over 5,500. Kepler was built to help determine the prevalence of Earth, like planets orbiting sun-like stars at the right distance, to have liquid water on their surface, a region often nicknamed the Goldilocks zone. While not a single extraterrestrial world has been a perfect twin of our own so far, researchers can use the sheer quantity of discoveries to make educated guesses as to how many might be out there. The current best estimates suggest that anywhere between 10% and 50% of sun-like stars have planets like ours, leading to numbers that make astronomers' heads swim. If it's 50%, that's bonkers, right? As Jesse Christensen, an astrophysicist at Caltech in Pasadena, California, say, there are billions of sun-like stars in the galaxy, and if half of them have Earth-like planets, there could be billions of habitable rocky planets. And that's really insane! But determining whether these planets actually contain organisms is no easy task. Researchers must capture the faint light from an exoplanet and spread it into its constituent wavelengths, scanning for signatures that indicate the presence and amount of different types of chemicals. While astronomers would like to focus on sun-like stars, doing so is technically challenging. NASA's mighty new James Webb Space Telescope is currently training its 6.5-meter mirror and unparalleled infrared instruments on worlds around stars smaller, cooler, and redder than our Sun, known as M-dwarfs. Such places might be habitable, but at the moment, nobody is really sure. For liquid water to be present on their surfaces, planets around M-dwarfs would need to orbit close to their stars, which tend to be more active than the Sun, sending out violent flares that could strip away atmospheric gases and likely leave the ground a dry husk. James Webb has been investigating TRAPPIST-1, an M-dwarf 40 light-years away, with 7 small rocky worlds, 4 of which are at the right distance to potentially have liquid water. The 2 closest exoplanets have already been shown to be devoid of atmospheres, but scientists are eagerly awaiting the results of James Webb's observations from the next 3. They want to know if even those outside the habitable zone can have atmospheres. There's special interest in looking for other planets around M-dwarf stars, because they are far more prevalent than sun-sized stars. and if scientists find them to hold atmospheres, that increases the habitable real estate of the galaxy 100-fold. Once we've found a planet that looks a lot like Earth, then we'll want to start hunting for chemical clues of life on its surface. James Webb isn't sensitive enough to do that, but future ground-based instruments like the Extremely Large Telescope, Giant Magellan Telescope, and 30-meter telescope, which are expected to begin taking data in the 2030s, could tease out the chemical components of nearby Earth-like worlds. Information from more distant targets will have to wait for NASA's next planned flagship mission, the Space-Based Habitable Worlds Observatory, expected to launch sometime in the late 2030s or early 2040s. The telescope will use either an external star shade or an instrument called a coronagraph to block the glaring light of a star and home in on dimmer planetary light and its potential molecular fingerprints. Which chemicals in particular astronomers should be looking for remains a matter of debate. Ideally, they want to find what are known as biosignatures, molecules like water, methane, and carbon dioxide present in amounts similar to what we find on Earth. What that means in practice isn't always clear, since our planet has gone through many periods when it contained life, yet the quantities of different chemicals varied wildly. But as a piece of good news, recently, there was much excitement when James Webb spotted dimethyl sulfide, a molecule that on our world is made only by living things on an exoplanet nearly 9 times Earth's size, located 120 light-years away. The results, which have yet to be confirmed, highlight the trickiness of such methods. If dimethyl sulfide is truly present in the planet's atmosphere, then starlight should also break it down to form ethane, a molecule that has yet to be seen. According to Kopparapu, no single gas is a biosignature. You need to see a combination of them. In 2022, Kopparapu and others in the community published a report emphasizing that any particular finding must be placed in the context of its stellar and planetary environment, since there could be many results that seemingly point to life yet have alternative explanations. This problem, how to definitively differentiate between life and non-life, is a perennial one, whether you're looking at distant planets or even phenomena here on Earth. Researchers may soon receive help from algorithmic techniques that can tease out associations too complex for the human brain to fathom. In recent experiments, Robert Hazen and his colleagues took 134 living and non-living samples, including petroleum, carbon-rich meteorites, ancient fossils, and a wasp that flew into their lab, vaporized them, and spread out their chemical constituents. Roughly 500,000 different attributes were identified within each sample's molecular makeup and run through a machine learning program. After the software was trained on 70% of the specimens, the technique was able to recognize with 90% accuracy which of the remaining samples had a biological origin. The device that is used to spread out the chemical components of the samples is around 7 inches long, small enough to be sent on missions to nearby ocean worlds like Jupiter's Europa or Saturn's Enceladus. NASA's Perseverance rover carried a similar instrument to Mars, so Hazen thinks his team's machine learning algorithm could be adapted to sift through its data and hunt for organisms past or present there. And because it relies on molecular relationships rather than detecting specific organic chemicals like DNA or amino acids, which may not be used in other biospheres, the method could allow scientists to look for life entirely unlike what we have on Earth. Such machine learning applications are also starting to find use in SETI, which has in recent years pivoted toward looking for a broader array of visible evidence for tool using extraterrestrial species than before. According to Sophia Sheikh of the SETI Institute, today most in the field are on the lookout for such technosignatures, defined as some remotely detectable signature of technology that we can characterize with astronomical instrumentation. This could be a radio signal, but other evidence could include things like optical laser pulses, giant space-based engineering projects, atmospheric pollution, or even artificial probes that make their way to our solar system. At the Zwicky Transient Facility near San Diego, California, which continuously searches the entire night sky for brief flashes of light coming from unknown sources, engineers are teaching artificial intelligence how to identify features that would not be expected from natural phenomena. As Ashish Mahabal, an astronomer and data scientist at Caltech, says, it's at that point that we can start asking questions. The answers to such questions could help reveal novel astronomical events, or just maybe, a star surrounded by enormous solar panels that feed an energy-intensive alien society. SETI researchers hope that by using such tools, they can help overcome some of their anthropocentric biases. Most recognize that our expectations of otherworldly beings are constrained by our own experience. For example, the search for signs of massive alien solar panels is often based on this assumption that there's always going to be an exponential need for energy. Because of all the avenues currently being explored, many scientists believe that answers to our questions about extraterrestrial life are not far off. But ultimately, the question of our cosmic loneliness is a philosophical one. For most of humanity's history, we didn't believe ourselves to be alone. We filled the heavens with gods, monsters, and mythic creatures. It is only in the modern age that our species has started to worry about its place in the universe. If we find intelligent, or even microbial, life beyond Earth, how will this affect humanity? Would we come together as one with the discovery that we are, in fact, not alone in the universe? Or would we lose our collective minds? Well, let's look at things objectively. First, finding extraterrestrial life would be comforting, since it would help soothe the concerns raised by the Fermi paradox. On the other hand, we don't think that it should dethrone humanity's place in the universe. We, like the animals and plants all around us, are the product of billions of years of evolution, and that in itself is incredible. And whether or not any other part of it harbors life, the cosmos is our home. We can choose to be lonely or to embrace the beauty and wonder all around us. In other words, if we find extraterrestrial life, we have enriched the story of the universe, not diminished ourselves. So, the hunt for alien life presses on. For now, SETI continues to scan the skies for radio signals, James Webb keeps blowing our minds with jaw-dropping images and data, the Mars rovers keep drilling holes near their landing sites, and future missions continue to be planned to explore the outer solar system for signs of life. And yet still, the question remains, are we alone? Perhaps one day, humanity will finally know the answer to this question. But until that day comes, all we can do is press on with our search. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. It has been several months since one of humanity's most accomplished spacecraft, the Voyager 1 probe, stopped talking to us. And though they remain somewhat hopeful, Voyager mission scientists are preparing for the worst, a goodbye. As Bruce Wagner, the Voyager mission assurance manager, said, sad and frustrated to have the spacecraft still working but muted. Bruce Wagner, the Voyager mission assurance manager, even though we know the end could come at any time, it's never easy to lose a spacecraft, especially one like Voyager 1. For more than 45 years, this boxy machine with a pearly white conical disc that sort of makes it look like a giant loudspeaker in space has been sending back stunning data. And I mean stunning. Not only is it the farthest human-made object ever, but it's also responsible for the identification of new Jovian moons, the discovery of yet another Saturnian ring, and the solar system's first and only family portrait that includes our eclectic gang of planets. It's also why we have the powerful pale blue dot image that resurfaces on the internet every so often to remind us of our insignificance, or rather, significance, depending on your perspective. As Carl Sagan famously said, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, has lived out their lives." The image of the Earth from a cosmic perspective, just a mere mote of dust suspended in a moonbeam, became nearly as memorable as the Earthrise photo taken by an Apollo 8 astronaut showing the planet as seen from the moon. The probe, which runs on nuclear-powered systems called radioisotope thermoelectric generators, kept flying. Our solar system has no clear boundary, but in the 2000s it crossed the termination shock, where solar wind particles abruptly slow below the speed of sound due to pressure from the gas and magnetic fields in interstellar space. Then, in the 2010s, it breached the heliopause, the boundary between the solar wind and the interstellar wind. With 4 instruments operating on Voyager 1, it now has a new job, measuring the magnetic field strength, the density of the plasma, and the energy and direction of charged particles in the environment they're traveling through. The purpose of the interstellar mission is to measure the sun's effects as we go further and further from Earth. We're trying to find out how the sun's heliosphere interacts with interstellar space, says Suzanne Dodd, project manager of the Voyager interstellar mission at NASA Jet Propulsion Laboratory. Voyager 1 is currently 15 billion miles from home, but for perspective, the nearest star is some 25 trillion miles away. It's a remarkable coda for its mission, decades after the probes completed their main goals. But the spacecraft has always had a secondary task, conveying a message to any aliens from beyond the solar system who might one day peek inside a craft. Both Voyager 1 and its twin, Voyager 2, carry a golden record, which looks like vinyl but is made of metal. A team of scientists and artists, including Sagan and Frank Drake, packed music, nature sounds, messages, photos, and more on each record. And they included players and instructions, should anyone find them. The ambitious project seeks to tell a story about humanity, what humans aspire to, and our world. It includes the music of Bach and Chuck Berry and images of families, homes, and scientific advances. According to John Lomberg, a scientific artist and the designer for the Golden Records team, the purpose of the record was to try to answer questions that we would have. What were the beings like who sent it? What do they look like? What do they act like? What was their world like? So it's really a self-portrait. Unlike the search for extraterrestrial intelligence, or SETI, the records are not designed to be a prelude to first contact. In fact, the Golden Records might be found millions of years from now, perhaps when human civilizations no longer exist. It's more like finding a fossil. You can't talk to the dinosaurs. This is a relic, our obituary in a way, the memento that we were once here. The Voyager probes were preceded by the Pioneer missions, which carried small metal plaques with symbolic messages. The pair of Pioneers left the solar system in the 1980s and 90s, but they're no longer functioning. Since then, no space mission has incorporated a similar record of humanity. Some say NASA's New Horizons, which flew by Pluto in 2015, offered another chance. However, that mission, as Lomberg says, was a missed opportunity, although it might still be possible to send a digital message to the spacecraft's computer. That would be durable, but it would not last as long as the Golden Records. The Voyagers have had a tangible influence on space exploration ever since. Their success inspired NASA and other agencies to revisit the outer planets, especially Jupiter and Saturn, and their myriad moons. These subsequent missions include Galileo, Juno, Cassini, and the European Space Agency's Huygens lander, plus new probes in the works, such as the Europa Clipper, Dragonfly, ESA's JUICE, and potential voyages to Uranus and Saturn's moon Enceladus. The Voyagers influenced pop culture, too. The first Star Trek movie in 1979 included an alien spacecraft called Voyager, which was actually an altered fictional Voyager 6. Voyager and the Golden Records have turned up in TV shows like Saturday Night Live, The West Wing, and, of course, The X-Files. The composer Dario Marianelli even wrote a Voyager-inspired violin concerto. The pair of spacecraft have lasted far longer than anyone imagined, and, Dodd says, the instruments are working and the data is still great. But they're showing signs of age. All this time, Voyager 1's cosmic letters have come through as computer messages often do, with zeros and ones in precise patterns. Through a little bit of handiwork, such sequences can be translated into words the human mind can grasp, and scientists were always excited to open a new package of Voyager 1's binary code. But then, in September of last year, the zeros and ones stopped making sense. The engineering team said that the call between the spacecraft and the Earth was still connected, but Voyager's voice was replaced with a monotonous dial tone. Glitches have happened to Voyager 1 before, such as in 2022 when the probe's attitude articulation and control system exhibited some complications, but this one seems to be a doozy. The team still hasn't been able to fix it up, even months since the issue revealed itself, and is actually still searching for the crux of the problem. So, is it time to call the final curtain on Voyager 1? Well, to that end, scientists aren't quite sure yet. They remain working to remedy the situation, and quite diligently at that. Voyager mission engineer Karim Badaruddin revealed in a recent statement that the team is tired because we have sustained a brisk pace for 3 months now, but we press on because we have ideas and we have hope. In December of 2023, the Voyager 1 team announced that the spacecraft's malfunction lies with its flight data system, which is one of its onboard computers. There used to be a backup flight data system, but that stopped working in 1981. Because of this issue, scientists are not receiving any science data or updates about the probe's health and status, including information that might reveal the source of the problem. Here's where perhaps the greatest trouble with this dilemma comes in. One of the flight data system's main jobs is to basically keep Voyager 1's medical records up to date, then work with what's known as the telemetry modulation unit to tell ground control what's going on. But because the flight data system itself is the one malfunctioning, that medical record transmission can't happen. The engineers said the team has attempted various simple fixes, such as resetting the flight data system to the state it was in before the issue began. This week, the team will send more commands to the spacecraft to gather information about the status of the onboard systems. In the coming weeks, the team expects to start making more aggressive attempts to reset various systems that might influence the flight data system. As of now, the team believes one possible cause of the issue has to do with the FDS's memory being corrupted by some mechanism that leads its binary code to sprout unintelligible patterns. However, engineers are also considering the fact that it could be a physical hardware failure. After all, Voyager 1's mechanics have been toiling away for multiple decades. Something could have simply broken down, hardware or software-wise. The anomaly has caused engineers to study and learn about the spacecraft. Much knowledge that was forgotten because it wasn't needed for many years has been recovered. As a result, it takes time for the team to understand how a new command will affect the spacecraft's operations in order to avoid unintended consequences. In addition, commands from mission controllers on Earth take 22.5 hours to reach Voyager 1, which is exploring the outer regions of our solar system more than 15 billion miles from Earth. That means the engineering team has to wait 45 hours to get a response from Voyager 1 and determine whether a command had the intended outcome. Thus, this repair process could take several months. But in a bit of a silver lining, the scientists have confirmed that Voyager 1 is exhibiting what's known as a carrier tone, which runs along a wavelength that doesn't carry information, but rather acts as a heartbeat. At the very least, we know it is alive. That means the spacecraft appears to be healthy other than the current issue. So if we can fix this, Voyager 1 should be able to continue its science mission. But the Voyagers are already operating far, far beyond what anyone expected of them. We know the more time that goes by, the more issues are likely to arise. We'll keep them going as long as we can, but we know they won't last forever. The spacecraft had a more enduring problem: their power supplies. Its radioisotope thermoelectric generator systems provide power by converting heat from the radioactive decay of plutonium-238 into electricity. But after 46 years, the fuel is now generating 4 watts less per year. NASA had turned off any systems and instruments not involved in the interstellar mission, and in 2019, it started turning off heaters in some of the instruments that are still running. That added a couple of years to the spacecraft's lifespan. Nevertheless, the Voyager 1 probe might only have a few years, or perhaps a decade, left in it. Eventually, its dwindling power won't be sufficient to run its instruments. At that point, the Voyager, in the words of Linda Spilker, who is currently serving as the Voyager project scientist, will become our silent ambassadors. As the spacecraft hurtle at 35,000 miles per hour into the unknown with its powered-down machines, it will still carry humanity's message in a bottle. In the words of Jim Bell, a planetary scientist at Arizona State University, and the author of a book on the Voyager mission's 40th anniversary, the golden record, a piece of human civilization, a piece of technology with a 1970s stamp on it, is going to persevere. It's not degrading, it's going to last for billions of years. It's going to outlast the planet that it came from. That is mind-blowing kind of stuff. Bell speculates that it might not be aliens, but our own descendants, who ultimately spot the far-flung spacecraft. And to be honest, that is not a wishful thinking. One day in the far future, we're going to be the ones who go find it when it becomes easy to travel and be tourists and see the Voyagers. At that time, we'll be thinking, wasn't that one of the most amazing things we did as a species in the 20th century? After all, Voyager 1's mission highlights the boundless curiosity of the human spirit and our relentless pursuit of knowledge. As it continues its journey into the unknown, it carries with it a message of hope, a testament to the achievements of space exploration, and a reminder of our tiny place in the vast cosmos. The end of communication with Voyager 1 will mark the conclusion of a remarkable chapter in human history, but its legacy will endure, inspiring future generations to continue exploring the universe. While engineers are working to extend the life of Voyager 1, James Webb Space Telescope has just found neutron star mergers forge gold in the cosmos. According to scientists, the observations of an unusually long blast of high-energy radiation, known as a gamma-ray burst, or GRB, made using James Webb and Hubble, allowed us to see gold and heavy elements forged, which could help us better understand how these powerful neutron star merger events generate the only environments in the universe turbulent enough to create elements heavier than iron, such as silver and gold, which results in a flash of light called a kilonova. Gamma-ray bursts, which are the most powerful explosions of energy in the known universe, have been associated with neutron star mergers before. But this discovery is different. These phenomena can be divided into 2 groups. On one hand, there are the long gamma-ray bursts that last over 2 seconds, and on the other, short gamma-ray bursts that last less than 2 seconds. While neutron star mergers have been associated with short gamma-ray bursts, long gamma-ray bursts were believed to occur as the result of the collapse of massive stars and not from such collisions. The extremely bright and long burst, designated GRB2300307A and detected by devices on board NASA's Fermi mission in March 2023, lasted 200 seconds. This marked the second most energetic gamma-ray burst ever seen. It seemed to be associated with a kilonova, designated AT2017GFO, and a neutron star merger that happened some 8.3 million light-years away, breaking the usual gamma-ray burst convention and challenging theories of how these blasts of high-energy radiation are launched. Stars are like stellar furnaces that forge the elements in the periodic table, beginning with the nuclear fusion of hydrogen to helium in their cores and continuing with the fusion of helium to heavier elements like nitrogen, oxygen, and carbon. The most massive stars, around 7 to 8 times as massive as the Sun, can forge elements all the way up to iron in their hearts. Once a stellar core is filled with this element, fusion ceases. That also cuts off the outward energy line that had been supporting the star against its own gravity for millions, or sometimes billions, of years. The cores of these massive stars then collapse under this crushing gravity, blowing away their outer layers in supernova explosions. This collapse transforms the stellar core, crushing electrons and protons into a sea of flowing neutrons, particles found in atomic nuclei that very rarely exist freely. However, in this sea, the neutrons are prevented from squeezing close together by a quantum principle called neutron degeneracy pressure, which can be overcome with enough mass to create a black hole. But sometimes there isn't enough mass for a black hole to come into existence. Those dead stellar cores, without the mass to overcome degeneracy pressure, are left as 12-mile-wide bogies, with masses between 1 and 2 times that of the Sun. However, there is a way that neutron stars can contribute heavier elements than iron to the universe. Not all neutron stars exist alone. Some traverse the cosmos in neutron star binary systems, meaning they have another neutron star in its gravitational clutches. As these dead stars orbit each other, they set the fabric of space ringing with ripples called gravitational waves that gradually carry away angular momentum from the system. This causes neutron stars to spiral together, emitting gravitational waves faster as time passes and leaking more angular momentum in tandem. Ultimately, the two collide and merge. This collision creates a gamma-ray burst and sends out a spray of neutron-rich material that help create the heavier elements of the periodic table. Other atomic nuclei around these collisions grab the free neutrons via the rapid neutron capture process, or R process, and become briefly lived super-heavy elements called lanthanides. Those lanthanides then quickly decay into lighter elements. This decay causes the emission of radiation, light we see from Earth as a kilonova. Thus, tracking the evolution of kilonovas can help follow the creation of elements like gold and silver. Over the course of weeks to months, Yuhan Yang, research team leader and University of Rome postdoctoral astrophysicist, explained that kilonovas span a wide range of behaviors. These behaviors depend on the composition of the ejected material and the type of remnant formed at the center of the merger site. Observations of most kilonovas do not extend to such late times in their evolution, but AT2017 GFO was different. Unfortunately, however, the late-time observational data for AT2017 GFO, collected with the Spitzer Space Telescope, were limited. They only offered weak signals contaminated by the kilonova's host galaxy and presented inadequate coverage in different wavelengths of light. These constraints had hindered scientists aiming to understand better kilonovas and the processes that create them. However, in the case of AT2017 GFO, the sensitivity and multicolor coverage of James Webb and Hubble observations allowed Yang and colleagues to observe the luminosity of this kilonova at late times. We tracked the evolution of the transient event associated with GRB2303U7A up to 2 months after the burst and captured the full blue to red evolution of this transient, which can be classified as a kilonova, Yang said. We discovered the recession of the photospheric radius at late times. The receding photospheric radius provides evidence for the recombination of heavy elements, such as lanthanides, occurring in the cooling process. Heavy R process elements are needed to produce the observed data. This confirmed that neutron-star mergers do forge elements heavier than gold, and even confirms that long gamma-ray bursts can come from neutron-star mergers. It hasn't solved the mystery of why this particular neutron-star merger launched such an unusually long gamma-ray burst. This event proves that a long-duration gamma-ray burst coming from compact binary mergers is not a fortuitous occurrence, Yang said, adding, "There are lots of questions to still answer about these events. What enlightening revelations can late-time observations of kilonovas offer on nucleosynthesis? We look forward to joint observations of long-duration gamma-ray bursts, kilonovas, and gravitational waves in the future, which will help unveil the mysteries about such outliers." A remarkable information: a lander is now circling the moon. The robotic Odysseus spacecraft, built by Houston company Intuitive Machines, arrived in lunar orbit on February 21st after acing a crucial maneuver. Intuitive Machines announced via X that Odysseus completed its scheduled 408-second main engine lunar orbit insertion burn and is currently in a 92 kilometers circular lunar orbit. After traveling over 1,000 kilometers, Odysseus is now closer to the moon than the end-to-end distance driving across Space City, Houston, Texas, the company added in another announced via X Today X post. Odysseus's time in lunar orbit will be brief. The lander will try to touch down near the moon's south pole on Thursday afternoon, no earlier than 5:30 p.m. Eastern Standard Time. Success would be historic. No private spacecraft has ever soft landed on the moon, and no American vehicle has done so since Apollo 17 in 1972. During its lunar approach, Odysseus notched another big milestone, snapping its first photo of the moon that we know of. Intuitive Machines shared that image via X as well. Odysseus, which is about the size of a British telephone booth, launched atop a SpaceX Falcon 9 rocket on February 15, carrying 12 payloads toward the moon. Half of them are NASA science instruments, which the agency put on board via its Commercial Lunar Payload Services program. This program aims to help NASA gather data that will advance the agency's Artemis program of crewed moon exploration by leveraging the capabilities of private American lunar landers. Artemis aims to establish a crewed base near the moon's south pole by the end of the 2020s. This region is thought to contain large amounts of water ice, which could be used for life support and be processed into rocket fuel to help refuel spacecraft on the go. Odysseus's mission, called IM-1, isn't the first commercial lunar payload services program effort to get off the ground. Last month, Astrobotic's Peregrine lunar lander took flight on the debut mission of United Launch, Alliance's Vulcan Centaur rocket. Peregrine suffered a serious fuel leak shortly after deploying from the rocket's upper stage, however, and Astrobotic ended up steering the probe into Earth's atmosphere on John 18. The other 6 payloads Odysseus is carrying on IM-1 belong to private customers, including Columbia Sportswear, which put some of its Omni-Heat Infinity insulative material aboard to give it a deep space test. Odysseus isn't the first private spacecraft to reach lunar orbit. For example, the Bereshit and Hakuto R landers, built by a private Israeli team and the Tokyo-based company iSpace, respectively. Both successfully circled Earth's nearest neighbor. Both, however, crashed during their touchdown attempts, Bereshit in April 2019 and Hakuto R in April 2023. That's all the information that we have for you today. And don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.